Okay, gang, guess what we're going to talk about today? Begin with M. End with magnetism. Try it. Magnetism. See these paper clips? I take the paper clips and I dump them out in the book. How come they're in the book and not on the ceiling? Gravity. The gravitational interaction between these paper clips and every molecule in the whole world pulling in which way? Okay. Down, right? There's this earth and there's mountains and everything, all pulls down, 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 down. How about the clouds? They pulling up a little bit? The ceiling pulling up a little bit? How many say, oh, there's no gravitational interaction at all with the paper clips in the ceiling? Show of hands. How many say there's a gravitational interaction between every pair of masses? Show of hands. Yay, my people, all right. So how come the ceiling, how come these things aren't moving up to the ceiling? How many say, I don't be knowing that, gee, I suspect they should. Come on, gang. What's winning, down or up? Down. Why down? There's a lot more ground down there than there is ceiling up there, so the net force is down. And the whole world is pulling these paper clips down against the book. That's a pretty good force, yeah? Watch this. See this little dinky magnet? How big is this compared to the whole world? Big or small? Answer begin with an S. Watch this. E. Now you know why Dick Tracy used to say, he who controls magnetism controls the universe. Look at the force of this little dinky magnet compared to the size of the world, pulling all these clips up. So we can talk about the magnetic force today, gang. The magnetic force. Ain't that neat? Okay, this is a pretty powerful magnet. Here's a pretty weak magnet. This one is suspended on a point. And it's magnetized. And what do we call it, gang? Do you know? Begin with C, end with umpus. Try it. Put it together. Compass. Excellent. That's a compass. And guess which way it's pointing? You know what it's doing? It turns out that the whole world is a great big, begin with an M. Magnet. And surrounding that world is a magnetic field. And guess what that compass lines up with? Begin with MF. The magnetic field of the Earth. And that magnetic field in this room is oriented like this. Okay? But what is the source of that magnetism? The source of that magnetism was betrayed years ago, more than 150 years ago, by a fellow by the name of Hans Christian Ørsted, who was a professor type teaching, I believe he was in a high school classroom. And he was showing the students that there's no relationship between magnetism and electricity. The physics books at that time had electricity as one subject and magnetism as another. And Ørsted was showing there's no relationship between the two. And one of the things he would do is he would line up the piece of wire like this and put it over a magnet and pass a current through it. And you really don't see anything happening. There's no interaction. Student came up after class, gang, and held it in this direction. Okay, watch this. When the current is passed over the wire like this, boom. You see that interaction? It turns out there's an interaction between a current-carrying wire and a magnet. And it turns out, to make a long story short, the source of all magnetism is moving electric charges. And when the charges move through the wire, they set up about the wire a magnetic field. And that magnetic field is in concentric loops around the wire. If I pass this wire through a hole in a piece of paper, and I put a whole lot of little compasses around the wire, and no current goes through, all those compasses would point north. But you know what would happen if I put a current through that wire? Bam! All the compasses will line up with the field. And it turns out that field takes the shape of concentric circles about the wire. The further away you get, the weaker they get, but the direction is all that way. So surrounding every current-carrying wire is a magnetic field that takes the direction of the concentric circles. The magnetic field about a bar magnet like this. You ever see the magnetic field of these things? If I put this down, put a piece of paper on the top, and then put iron filings, you'll see all the iron filings piling up in the middle, betraying the shape of that field. You have photographs of that in your book. So the magnetic field is very strong between these pole pieces, and it's also relatively strong about a current-carrying wire. The more current through the wire, the stronger the field. Hey, guess what, gang? If I take that wire and I loop it over like that, guess where the field will be concentrated? How many say, oh, probably out here somewhere? Show of hands. How many say, oh, the field would probably get all concentrated right in here, all bunched up in here? Show of hands. How many not be knowing? Okay. Well, it turns out, yeah, the field will get all bunched up inside here. And furthermore, if I put a piece of iron through there, guess what the iron will turn into? Or guess what the device is called? Begin with EM. Electromagnet. And I can kind of show you that over here. Here I have a whole lot of coils of wire. See all those wires, these green coils? It's coiled around, 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 around. When I pass an electric current through here, guess where the field is going to be concentrated? Inside or outside? Begin with an I. Inside. It's going to be concentrated in there. And furthermore, what I'm going to do is I'm going to induce the magnetization of this piece of iron core. I can show you that. Right now, this does not pick up the clips. Why doesn't it pick up the clips? It doesn't pick up the clips because right now it's not an electromagnet. Why is it not an electromagnet? What are the two ingredients you've got to have for electromagnet? Electro, honey. I've got to put some electricity. I've got to put some current through here. And I can do that by simply plugging into a power source here. Can you hear that little hum? Turns out this is alternating current. But let's watch this, gang. It turns into a magnet. Guess what kind of magnet? Electromagnet. Get it? And this electromagnet is what? This electromagnet is simply a device that concentrates the magnetic field line in a coil, and then you put a piece of iron in there, and the iron becomes magnetized by induction. And now it cuts off. Oh, look at this. A little residual magnetism. That's a fancy word for leftover magnetism, okay? It turns out these are still a little bit magnetized. Hey, you want to screw up a magnet? Drop it on the floor a few times, or throw it up against the wall, or put it in a fire. Would that be good for a magnet or bad for a magnet? Why bad for a magnet? Because you're going to jostle all the alignment out. You guys be reading about the alignment of the magnetic domains. We don't have time to talk about that today. In all these lectures, don't we just talk about some of the icing on the cake? And you guys get the cake in the textbook, yeah? But all those domains are all lined up for a permanent magnet, right? That's the difference between this piece of iron, which is not a magnet now, and the piece of iron over here. Here, they're all lined up. Not all, but many are lined up, nice and permanently, okay? This kind of iron, such way. This, no. Not until I power it up with electric current. So, hence we have electromagnets, and the name of the game so far is the source of magnetism are moving charges. Moving charges. If they move in a wire, then you wrap that wire around, you can concentrate the field lines, and you get an electromagnet. Any questions at this point? Lee?
How did the moving charges, or which moving charges cause the magnetism in the natural magnet?
In the natural magnet, one could say, very good point. Where are the moving charges? There's no current. But the iron magnet is made out of what? Atoms. And atoms are made up of what? Charges. Charges in the nucleus, okay, which don't move very much, okay, and charges which orbit around, and those are the electrons. Those electrons, gang, make up little electric currents. But in most atoms, and this is in your chapter, in most atoms you have as many going one way as the other way. Turns out the spin of the electron is even more important. You have as many spins one way as the other way, and one effect cancels the other, and so net effect. But there's one there's one atom in the periodic table which has what physicists say a net spin of 4. 4 more spins one way than the other, so you get a net effect, and guess what that element is? Iron. That's what iron is. And that's why you find iron is said to be ferromagnetic, getting into that kind of thing. I want to show you something that's even more interesting than what we've seen. Let's take this magnet. I'm going to put the wire in the magnetic field of this magnet, and I'm going to touch this momentarily so I get a pulse of current. And when I do that, when a current goes through this, would this wire, in a sense, be a magnet? How about when no current goes through it? See, it's copper wire. Copper is not ferromagnetic. Copper, you've all tried when you were a kid to pick up a penny with a magnet. It doesn't work, does it? Because the penny's copper, okay? So the only way you're going to get magnetism with copper is to have, boom, electrons flowing through it. Electrons flowing through anything would set up a magnetic field around that anything, yeah? Let's see what happens with the magnetic field of the wire and the magnetic field of the magnet. Let's see if there's any interaction. What do you suppose? Watch this, gang. You see that jump down? See that jump down? Let me turn the magnet around. Jumps up. Did you see that? I'm going to do it one more time. Watch. Wow, jumped up. So one way it jumps up, and the other way, put it this way, it jumps down. I wonder if that jumping motion could be harnessed. How many people say, well, no, there's probably no practical application of that. Wires will move in magnets. Big deal, right? Is it a big deal? It's a very, very big deal. Because guess what this underlies, gang? Electric what? Begin with M, end with odors. Try it. Motors. Any electric motors be working on such principle, okay? And dig this. Whenever you see any electric motor, realize, you know, sometimes we see things and we're so overwhelmed with the complexities we don't know what the nitty-gritty is. Realize the nitty-gritty of an electric motor is simply a current-carrying wire, boom, being deflected in a magnetic field. Period. That's it. Motors operate that way. Okay? Now, let's suppose I take this wire and I put it like this through there, okay? I'm not going to take the trouble to do that right now. But if I put it like that, then the current's going this way on one wire, but doesn't it go the opposite way on the other wire? I want to have you use your mind here. What's going to happen to this thing if I pass current through it? Now, one side will jump up, and the other side will, which is going to produce a twist. Do you see it's going to twist? And the more current flowing through it, the more it will twist. And guess what we have here, gang? Can you see down below here, I have a magnet and I have a copper coil inside? I don't know if you can see that, gang. You've got a magnet here, a permanent magnet, and a copper coil inside. And when current goes in that coil, it comes this way in one loop and this way in the other. One part is pushed up, the other part's pushed down, and the whole contraption is attached to this needle. And when the little coil twists, guess what the needle does? It also twists because they're connected. And the more current that flows through it, the more it's going to twist. Does that make sense? Now you know how a meter works. A meter is simply what? It's simply a coil of wire. Here I've got a coil of one loop in a magnetic field. When a current flows through it, part of the coil is going to be pushed down, part is going to twist. Hey, it makes sense, doesn't it? The fact this wire will jump up one way and the other way jump down leads you right into seeing the connection with how a meter works. We get that? Can we take it a step further? How many people say, no, that's enough, information overloaded. No, come on, we can go further. What would happen if, when I put a current here, how would it twist? This way or this way? It depends on which way the current flows. And if I put a strong current in, it'll twist a lot, a little current a little, okay? But can I make this thing rotate around and just keep rotating and rotating and rotating? No, I can't do that. You know why? Because there's no way that I know here to change the direction of the current as you do it. But if I get this thing, so hey, look at this, gang. If I get this, so when it makes a twist and boom, it's full scale deflection, okay? And then the current turns around and goes the other way, then it'll twist again. And then again. And then again. And again. I get a motor. And that's what a motor does. A motor reverses the direction of current in the coil every half turn. And that's what happens. Here we have one right here. Here's a motor here. What we have here, a little bit more complicated. See, I have the electromagnet down here. Electromagnet. And up here's my magnet. Okay? So I've got a magnetic field in here. All right? Now what I'm going to do is I have a coil of wire here. See this coil of wire? If I get current flowing through that coil of wire, maybe up here the current's going this way in the magnetic field. Okay? So it gets blown down maybe. But over here the current's going this way. It gets thrown up. So it, boom, it twists. But up here it would stop. But what if I change the direction of the current? So here now overshoots a little bit, and this gets pulled down, this gets pulled out. Bam, 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 bam. If I change the direction with every half turn, I can change a meter movement into a motor movement. And I do that with this little device here called a commutator. I'm not going to take the time to get into the detail of it, but there's a little split ring there. So the current maybe feeding in here now goes to this particular way, and when it turns one halfway, whoop, then it slips over to this other electrode and does there, dan, dan, dan. Suffice to say, every half turn, the current will change direction in the coil. When that happens, the forces on the coil change direction, and guess what's gonna happen again? Now, nobody here really gonna get excited about this, but could you put yourself about 150 years ago and then be thinking about this thing? And then someone shows you something like this. You'll see why people were excited. What I'm going to do now, gang, is I'm simply going to attach this electromagnet to the battery, because I want to have I want to have current in the coil to make that a magnet. And when I do that, then I'm going to pass current through this coil. And what's it going to do? Yes. And then put on here like that. Now I get current going on there and current going through there, and I should get a... You know how sometimes when you're shaving, you got to get the thing started a little bit? Eh? Look at that. What do we see there, huh? How many people are bored? Would your great-grandfathers and grandmothers be bored about such a thing? Would they? They would say, hey, because of this. Do you suppose this had any difference in the way the world works? Gang, it really did. If it weren't for things like this, these devices, you know, people's teeth would be all green. You know, when you see your friend, you smile, and one of the things that's nice is a nice sparkly teeth, right? Without one of these things here, everyone would have green, scummy teeth. You know why? Because there'd be no such thing as an electric toothbrush. Yeah. You see, people are rather healthy today. People are rather healthy. Do you know how people would be if they didn't have motors like this? They'd be emaciated. They'd be undernourished, because there'd be no electric can openers. There'd be no way to open cans of food. Okay, you hear what I'm saying? Okay. You see people that their clothes are lint-free. If it weren't for devices like this, you'd have no little lint machine to take the lint off. The world would be different without this electric motor. This electric motor adds to the quality of life. Will you agree? Huh? Think about the electric motor every time you see someone with a nice clean smile. All right? Yeah, really changes things. Questions, Lee?
If the current didn't alternate, would the motor keep spinning?
If the current didn't alternate, it would just turn to one point and stop.
Or would it go a little beyond and then be...
It might shoot, it would go something like this, and finally set up. Just like maybe putting a compass in a magnetic field and seeing and finally settle off. See? But it's got to reverse to go the other way. Isn't that nice? And a little simple device that'll do that. So what we've talked about so far, gang, is how we can begin with magnetism and electricity and get motion. Okay? With those two things, we can get motion. But before I go further, I think there's another question.
How come if one's charging it to go one way and one of the wires is charging it to go the other way, how come does it cancel out and just get it to stop?
Well, bear in mind now, let's look at this. I don't know if I'm answering your question, but let's suppose the current's going through this way. This side is being pulled up. This side is being pulled down.
Oh, okay.
So it twists. Now when it gets to here, boom, the current changes. Okay? Because I've just gone from a little space to here. Whoop, the current goes the other way now. How this happens would take a little detail for you to look at. And I'm not going to explain it too much. I used to explain this on the board. It takes 10 minutes. And then you forget anyway. Suffice to say, this little thing called a commutator will reverse the direction of the current. And when it does, then what pulled it up will now pull it down, and boom, 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 and away it goes. See? So there's not a cancellation. There's a reversing of direction and a continual rotation.
What determines the speed of it?
The speed, what determines the speed is the strength of the current, or the strength of the magnetic field. See? The stronger the magnetic field, then the greater the interaction. The more the current in here, the greater interaction. So if you increase either, you'll increase the speed at which this thing goes. Because a small force will pull it up a little bit. A big force, boom, snap it up quickly, see? And bam, 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 bam. Bigger force will make it go faster, faster, faster. Most motors are designed to rotate so that at 60 times per second. 60 rotations per second. Okay, that's 60 hertz. 60 hertz motors. That's what we have in this country. In Europe, they have like 50 hertz motors. But there's a particular frequency at which the motors are designed to rotate. Okay, gang, I'm going to shift gears a little bit. If from electricity you can get magnetism, the question was raised a little over 150 years ago, can you go from magnetism and get electricity? And the answer is no, there's no way to do that. Does that bother you a little bit? Yeah. Come on, gang. Is there a way to... Is nature symmetric? Yeah. How many people... Oh, no, nature will go from here to there, but that doesn't mean it'll go from here to there. Hey, how about it? Come on, think. Check your neighbor. Can you go from magnetism and get electricity? Okay, gang. How many be saying, yeah, it's probably so that you can go from magnetism and make electricity? Show of hands. Well, almost. Oh, okay. All right. Okay. All right. All right. We're all together, yeah? Okay. All right. Let's see how that was done in 1831. This was done by a couple of physicists about the same time in history. One was Michael Faraday, a Scottish guy in England, and the other was Joseph Henry, an American type in Vermont in the 13 colonies. And they both at the same time found the same effect. And here's what they discovered. They had meters similar to this at that time, but they didn't know how to get electricity. Well, they got electricity from batteries. A fellow by the name of Volta, Alexander Volta, Italian type, made batteries, and that was kind of nice. Everyone was excited about electricity. And then Michael Faraday and Joseph Henry discovered the following. No batteries. Batteries over there, gang. No batteries, no tricks. Magnet, wire, meter. Watch this. You see anything?
No.
Faraday didn't see anything either. Okay. And but watch this. Henry didn't see anything either, but watch this. Did you see something? Yeah. Again. My goodness. My goodness. There's no battery nearby, and guess what we are generating? Begin with EC. Electric current. I am generating electric current. And Faraday and Henry found out that. No batteries, no cells, no lightning, none of that. Just the motion of a wire in a magnetic field. So Faraday goes to bed, and he's really excited about that. And while he's in bed that night, I'm making this up now. While he's in bed that night, he's kind of thinking, gee, I wonder what would happen if I did it with 2 wires. So he gets up in the middle of the night, takes his candle, goes downstairs. Had to do a candle. Little did he know that he was going to get rid of candles, honey. The candle industry was furious later on, okay? Because what he did is he went down and he took 2 wires, and guess what happens with 2 wires, gang? Twice as much current. Goes back to bed. Then he thinks, I wonder, 3 wires. Shall we try it? Didn't sleep the rest of the night, gang. I wonder, 1,000,000 wires. What do you think? 1,000,000 times as much. Okay? This was a remarkable discovery that one can, it turns out, induce voltage by simply moving a wire in and out of a magnetic field. And so Faraday's discovery is couched a little differently. Today it's called Faraday's law. And what it says is this, a little more complex. Change the magnetic field in a closed conducting loop of wire. Doesn't even have to be conducting. Just change the magnetic field intensity in a closed loop, and you will induce a voltage in that loop. Now this loop happens to be a copper wire, so the voltage in that produces a current. So look at this. You get a current. Change the magnetic field in 2 loops of that closed copper wire, 2 loops of that circuit, and guess what you get, gang? Twice as much voltage. 3 loops, 3, da. So that's the rule. All you got to do is change the magnetic field intensity, and you will induce a voltage, which will produce a current if you're talking about a conductor. Ain't that neat? That is really, really nice. Now we can produce electricity. So you know how all of Europe started converting to electricity. They started having lamps and all that stuff, and they had all these kids up on the hills going like this. Okay? And these kids are all doing this thing, okay? And one day they say, hey, we're getting tired doing this. See that waterfall coming down? Why don't we put this wire on a great big piece of wood and have it rotate, huh? By the waterfall, put a little paddle wheel, and we'll go home and get all the electricity. And that's, of course, the start of the Industrial Revolution. I'm making that part up, but you get the idea. All you got to do is rotate the loop in a magnetic field, or just plop in and out of the magnetic field, and there's your electricity. Faraday's law. Got such thing? Questions?
It seems that the characteristics of electromagnetism and gravitation are similar. Yet, from what I understand, they haven't been able to quite figure out what gravitation is. Am I right in thinking that?
Yeah. Yeah, of course, Einstein spent most of his life trying to find the unification of all the forces, you know. And they still haven't, they meaning the physics type, still haven't found that magnetism or electromagnetism and gravity have a commonality. That has not been found, if it's there. If it's there. Let me say this, though. It seems like there's two different things going on here. When I first learned about this, I thought I learned two different phenomena. One was, if a current flows through a wire, it's deflected. And then a completely different one was that if you take a wire and plunge it out of a magnetic field, you'll induce current. But you know what? They're one and the same. There is a commonality there. Let's look at it. If it's true that electrons going through a magnetic field, crisscrossing, will be deflected, then it ought to be true that you can generate electricity by doing this, because it's one and the same thing. How fast do the electrons travel in a common circuit compared to the speed of light? Fast or slow? Slow, about a snail's pace. Did you pick that up in the study of electric currents? The actual drift speed of the electrons is very, very slow. The signal traveling through the wire, that's about the speed of light. So when I have current coming through here, when you saw that deflected out, the electrons did not go racing through at the speed of light through the wire gang. They're probably going like this. And that motion through there, boom, you had the interaction. Now, if electrons moving this way are forced up, what would happen if I just take the electrons and force them down? Or just move them down? They're going to be forced perpendicular. But this time, guess what's along the perpendicular direction? Begin with W. Wire. There's a path. So when the electrons are coming down, they're again deflected. I could go like this, I could go like that, the same thing. They're deflected. This time, they shot up before, there's nothing to do but pull the whole wire up too. But if I come in this way, boom, they shoot up, but they go along the wire. So what I've done is I've produced a current. So this over here produces an electric pressure on there, which we call a voltage. And so a voltage produced in a wire crossing through a magnetic field is not fundamentally different than having electrons go through a wire held this way and being popped out the side. It's the same thing. Check that part in the book. It's the distinction between the motor effect and the generator effect. They're really one and the same physics. Check that out. Now over here, we have a generator. Turns out this is a generator too. I take the time to do this. Well, I'm not going to take the time to do this, gang, because I got too many ideas to talk about. But with this, what I would now do is I would now hook up the electromagnet, and I wouldn't put any hookup with this, the coil, with the battery at all. I'd make that an electromagnet, and then I'd hook this up to the galvanometer and turn this, and guess what you're going to see over here? It's the same thing as just like twisting it in here, okay? You're going to see current produced, okay? I'm not going to take the time to do that. I can kind of show you this because it's already hooked up. I think you've seen this before. Look at that. I'm lighting up the lamp, okay? Now I'm generating electricity to light up the lamp. See if you're sitting next to someone who knows how is it I'm able to generate electricity and light up that lamp by turning the crank. What is going on? Okay, gang, how about it? How about it? What is going on? How am I generating electricity over there? What am I doing? What's Faraday say you got to do?
You have to have a magnet and move wires.
I got to change the magnetic field intensity in some closed loop of wire, yeah? And guess what's inside here, gang? Begin with closed loop of wire. And when I take that closed loop of wire and I rotate it, Guess what I do to the magnetic field intensity? If I'm holding my arms out like this and it's raining and the rain's coming straight down, boom, right through my arms. I got a lot of rain coming through my arms, yeah? How about I turn like that? How much rain coming through? None. Okay, how about I go like that? Some. I mean, I can't keep doing it. You see what I'm saying? But I could clip the amount of rain that I'm. You see what I? Same thing over here. In the magnetic field, you're rotating a loop. You're changing the magnetic field in that loop, honey. You're getting a voltage, and that voltage light up the lamp. You see that, yeah? I mean, it's just not an interesting little gadget here. I want you to see what's going on with it, huh? Okay. Here's a piece of aluminum. Aluminum, does it have magnetic domains in it? Answer begin with an N. No, very good, okay. No magnetic domains. But watch this piece of aluminum, which is not a magnet now. Is this the first time you've seen that? Remember that. Do you know how we put things in orbit now? The way we put things in orbit is we take a rocket and we and it keeps picking up speed and finally goes into orbit. Okay? But what are we going to do in the future? Well, you can't do it with people inside, gang. But if you want to get something into orbit, okay, instead of a gradual acceleration and a pickup in speed, they'll be doing this. So today, remember today's the day you first saw that. This is a very, very serious candidate for propelling things from the Earth up into orbit. Okay, yeah, electromagnetic propulsion. Now, why did this thing fly out, gang? Should I leave that as a question for you? How many would have the next few days completely spoiled by not having that information? Why did this thing fly out? Why did this all of a sudden become a magnet? Maybe there is no reason for that. Maybe it's just one of the strange things about the world. Now, let me ask another question. Let me go like this. I held it way down here where the magnetic field was strong. Let's suppose I just put it there. Electromagnetic levitation. How come that thing is levitating? Why? This becomes a what when I plug it in? Begin with M. Magnet. And this is levitating, so this must become a... But it's aluminum. But it's a closed loop of aluminum. It's a closed loop of aluminum in a changing... Oh, I'm starting to get it. Let's see, this is a changing magnetic field because it's AC. And there's some connection between a changing magnetic field and a closed loop. You guys be getting it? No, I guess there's no connection. Or is there? How many know why this thing was levitating? Did you ever see one magnet repel another? What did you just see now? You saw one magnet repel another. And why did it fly off when it was way down here? Here's a question you can all answer. Every one of you guys can answer this. This thing weighs 1/8 of an ounce. I'm making it up. 1/8 of an ounce. What is the strength of the electromagnetic force pushing up on that ring? Check your neighbor. What's the answer, gang? 1/8 of an ounce. That's old mechanics, right? If there's 1/8 of an ounce pulling down and there's something pushing up to be keeping equilibrium, that up must equal the down, and that's 1/8 of an ounce. Ted Bradstrom has some ideas of electromagnetic induction he wants to share with us today.
Speaking of electromagnetic induction,
He's got a nice one here. Very simple, really nice.
magnet, coil. So we know if we move a magnet through the coil, what's going to happen? Hopefully we get current flowing. Okay. Goes through the wire, meets another coil. What happens when you get a current through a coil? Magnet. Okay. So we put a compass in the middle of this. And, okay, let's see if we get it. There we go.
Look at that, gang. Look at that.
Okay.
An interaction from here to there. Yay.
Just in case you think we were lying, I'll just move this, and you can see how it's moving, right? Is the
Nothing
compass
moves down
moving?
there, yeah? Now watch when he changes the magnetic field in the coil. What happened down here, gang? Yay. All right? Okay.
You want to know the fun part? You don't have to move the magnet. You can hold the magnet steady
Yeah.
and move the coil back and forth.
Hey, you know what? You know what is a neat application of electromagnetic induction? It's just been the last few years, and that's the smart lights. When you're traveling down the road and you're coming to the traffic light and the lights change for you. You drive over something and that something changes the lights. They used to put like a piece of rubber tubing out there with compressed air and it would boom, make a little pulse of air and that changed the light, but then the rubber would wear out. What they do now is they bury in the road a coil of wire. Okay? Coil of wire buried in the road. Now, through that coil of wire is a magnetic field of the Earth. And part of that field is in that Earth, all right? Now, if you could change the magnetic field intensity of the Earth through that big coil of wire, what would you induce in that coil? Begin with a V. A voltage, isn't that right? So when your metal car drives, when your iron car, a wooden car won't work. When your iron car goes over that coil of wire, does it not alter a little bit the magnetic field intensity in that loop? Answer begin with a Y. And when it does that, it makes a little tiny electric current which activates the switch of changes the lights. Isn't that neat? So the next time you're driving near traffic lights, look down to see if someone hasn't putting down there a couple of coils of wire. Of course, you get two to make sure, huh? Check that out. Another thing, too, tape recorders. Tape recorders. What does a tape recorder do? Well, in a tape recorder, when you speak into a microphone, you get a little plug like Ted had to go back, forth, back, forth, and makes a little vibrating current in wire, right? What if that is passed down to a little electromagnet, and you drag by that electromagnet some rusty tape, and the rust is iron oxide. When that iron oxide slides by that magnet there, varying strength, you get on that tape then varying strength of magnetism. Some is magnetized a lot, some magnetized a little bit. And the little vibrations you're getting on the tape. Now you take that tape and bring it to another machine, I won't tell you the same machine, and drag that tape at the same speed past an empty coil of wire. What's going to happen to the magnetic field intensity in an empty coil of wire when that tape drags by? It's going to change. Isn't that right? And if a piece of tape comes by that's heavily magnetized, boom, you're going to get a big pulse of current. A little tiny bit, well, you can get variations. And isn't it amazing that that tape driving by there, the empty coil, the variations in the magnetism set up variations of voltage in that wire, Faraday's law, which then goes into driving a speaker, again, the plug going back and forth, glued to a what? A paper cone. And the paper cone vibrates the same way, and boom, you get music. So look, next time you look at your tape recorder, honey, what's underlying all of that? It's EMI. What are we talking about? Electromagnetic induction. Ain't that neat? Now I got one question to leave you with. I got two questions. Number one was, how did this thing, boom, fly off? What's the basis of that electromagnetic levitation? And the other question is when I crank this generator, it's harder to turn when it's lit up and easier to turn when it's not. Right now I'm turning only against friction. But when I hook it in and it becomes part of the circuit, it really is more difficult to turn. HC. How come? Think about that. It's physics, all right? Yay.